This lesson is over polynomial functions. We know linear and quadratic functions, but they are part of a larger group of functions called polynomial functions. Polynomial function is represented as p of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 power plus plus a sub 1 x plus a sub 0, where the following holds true. The coefficients are real numbers and the exponents are whole numbers. Now in this case, the coefficients are the a values in front of the x, and because it says coefficients are real numbers, that includes positive, negative, fractions, decimals, radicals. Now for exponents, those are just whole numbers. Your whole numbers are 0, 1, 2, 3, 4, and so on. Whole numbers do not include fractions, nor do they include negative numbers. Now, to make more sense of what exactly is a polynomial function, let's look at an example. If we were to have the polynomial function p of x equals negative 7 x to the 5th plus 3x to the 4th plus 17x cubed minus 11x squared plus 5x minus 23. The leading term is known as the term with the highest exponent. In the generic form, that's represented as a sub n x to the nth power. Now, to make more sense of it, looking at our example, our leading term would be negative 7x to the 5th. Next, let's look at the leading coefficient. The leading coefficient is the number part of the leading term. We would call that the a sub n. But in our example, our leading coefficient would simply be negative 7. Next, we find the degree. The degree simply means the highest exponent. Well, in the generic form, the highest exponent is represented by n. But in our example, our degree is a 5. Example 1, complete the chart. And so we have 5 different columns. The first column identifies the function. The next column wants the leading term. The next column, the leading coefficient. Next would be the degree. And the last column is the type. And so we're going to look at several examples. For A, we have f of x equals 3x minus 2x squared plus 7. For B, we have g of x equals 8x plus 5. For C, h of x equals negative 4. D, f of x equals 5x squared minus 6x to the 4th plus 2x. E, f of x equals x squared minus 11x plus 9x cubed. All right, so looking back at the A, example A, we want to find the leading term. Now, keep in mind the leading term does not simply mean the one in front, it means the one that has the highest power. And so for A, our leading term is negative 2x squared. Now looking at the leading term, we identify the leading coefficient, which would simply be negative 2. Again, looking at the leading term, we want to identify the degree, which simply means the highest exponent, which is a 2. And then the type means, well, how would you classify this? Is this linear? Is this cubic? Like, what would you call this? Well, if the highest exponent is a 2 or an x squared, that does mean this is a quadratic. Looking at B, we need to identify the leading term. And in this case, it would be 8x. The leading coefficient would be 8. The degree, well, means the highest exponent. In this case, we see x, but we do not see an exponent, but there's an understood imaginary 1 there. So its degree is called a 1. And then the type, well, since we see 8x, that does mean this will be linear. For C, we look at the leading term, or in this case, the only term, which would be -4. Next, to identify the leading coefficient, well, the coefficient is the number part, which is still going to be -4. For the degree, we need to look at the highest exponent. In this case, because you do not see a variable, it's understood to be x raised to the power of 0. Because we know anything raised to the power of 0 is equal to 1. So there is an imaginary x raised to a power of 0. Although we don't see it, it is there. And so the type, well, this is considered constant. Since -4 is a plain number, this is going to be a constant, which simply means this would be a horizontal line. Not increasing, not decreasing. Instead, it just remains constant. For D, to identify the leading term, we find -6x to the 4th. The leading coefficient would be -6. The degree, the highest exponent, would be 4. Now for the type. We haven't seen this type, so this may be new. If you think of the prefix, what kind of prefix represents 4? Well, what about quarters? In this case, this is called quartic. Just like we need 4 quarters to make a dollar, this is considered quartic. For E, the leading term would be 9x to the 3rd. The leading coefficient would be a 9. The degree would be 3. And then we classify this as a cubic. Now we're going to talk about characteristics of polynomial functions. All polynomial functions are considered continuous, smooth, and the domain is all real numbers. Now, what does it mean to be continuous? It means there's no holes or breaks. In other words, I should be able to draw the graph without having to pick up my pencil. For smooth, well, that simply means there's no sharp corners. And then domain is all real numbers means I should be able to use any x values that I want. So let's look at a few examples of polynomial functions. Here's 3 different graphs that all are considered continuous, smooth, and where the domain is all real numbers. Now let's look at some non-polynomial functions. In this case, if you look at the first graph, notice it has a sharp corner, which means this is considered not smooth. For the second graph, notice there is a break. You would draw the first part of the graph, pick up your pencil to relocate it to finish it, which means this is not continuous. And in the last one, this one, the domain is not all real numbers. There is a value to where x is not included. So these are all separate examples of non-polynomial functions. Now let's look at determining end behaviors. To do that, let's look at what we do know. Here's a graph of y equals x, a graph of y equals x squared, a graph of y equals x cubed, another graph of y equals x to the 4th, and a graph of y equals x to the 5th. And what we're looking at is the end behaviors. So looking at the first graph, what happens on the left side? Well, notice the arrows going down. What happens on the right side? the graph is going up. So we say the end behaviors of y equals x is down on the left and up on the right. Let's look at the next graph. On the left, we see the graph going up. On the right, we see the graph going up. So for y equals x squared, the arrows are both going up on the left and right side. Go ahead and continue looking at the remaining graphs, identifying its end behaviors. Hopefully you found the same patterns as I did. But do you notice any patterns? Look closely. It turns out there is a pattern. There's a pattern for when there's an even degree, and there's a pattern when there's odd degree. So looking at your even degrees, that means your x squared and your x to the fourth. What do you notice about their end behaviors? Well, in this case, they're both facing the same direction. Specifically, they're facing up. So all even degrees will have arrows going the same direction. Could this graph potentially face down? And the answer is yes. If our leading coefficient had been a negative would make it flip or reflect across the x-axis, so then they would both be facing down. Now let's look if it's an odd degree. So look at the odd exponents. Y equals x cubed, y equals x to the fifth. If they're odd, they tend to go in opposite directions. Now, if we were to have a negative coefficient, that would cause a reflection, which means from the left side, instead of it going down to up, it now would go up to down. It would reflect the directions. So let's look at an example. Example 2 says state the end behaviors of the function. For a, we have f of x equals negative x to the sixth plus 3x to the fourth. So to state the end behaviors, we have to find the leading term. Our leading term is negative x to the sixth. And so we look at the degree. Is this even or odd? Since it's even, we think they'll be going the same directions, both facing upwards. Now we take the time to look at the sign. Since it's a negative x to the sixth, that means our directions will flip, which causes the result to be facing downwards. So our end behavior would be down on the left and down on the right. For b, we have g of x equals negative 3.5 x to the fourth plus x to the sixth plus 0.1 x to the seventh. Again, to identify the end behaviors, we must find the leading term, which in this case is 0.1 x to the seventh. We look at the degree. Notice it's odd, which means we're thinking they're going to be going opposite directions. Down on the left, but up on the right. Now we look at the sign. Since it's a positive, it will not flip, which means the end behaviors will remain down on the left and up on the right. For c, we have h of x equals negative 4x cubed minus x plus 6. We identify the leading term as negative 4x to the third. Because it's an odd degree, we think they're going to be going opposite directions, down on the left and up on the right. Now we pay attention to the sign. Since it's a negative 4x cubed, that means it will flip or change directions, which means the end behaviors will be up on the left and down on the right. Now let's recall, what is a zero of a function? Well, it's a blank of the equation, and it's in blank of the graph. Well, when you're talking about a zero of a function, that means you're talking about a solution of the equation, and it means you're talking about an x-intercept of the graph. Example 3, determine whether -2 and 2 are zeros of the given function. G of x equals x to the fourth minus x cubed minus 3x squared plus 5x minus 2. So when it says determine whether -2 is a zero of the function, it simply means we will plug in -2 in for x. When we plug in -2, we must now obey the GEMS or order of operations. So first we have to deal with the exponents. -2 to the fourth is -2 times -2 times -2 times -2, which gives us 16. -2 cubed is -2 times -2 times -2, which gives us a -8, but keep it inside the parentheses. The next exponent is -2 squared, which gives us a +4. Again, keep it inside the parentheses. We've now completed all the exponents. Now we're ready for multiplication division. As we move left to right, first we see the opposite of -8. The opposite of -8 creates a +8. Next we see -3 times 4, which creates a -12. Then we see a 5 times a -2, which gives us -10. Now that we've done all the multiplication division, we're ready for addition subtraction from left to right. 16 plus 8 is 24. Bring everything else down. Next we see 24 minus 12. Well, that's 12. And we bring everything else down. Next is 12 minus 10. That is 2. Bring everything else down. And then the last step, 2 minus 2, is 0. So we've plugged in the -2. We have a result, but we have to answer the question. Determine whether -2 is a zero of the function. That simply means when I plug in a -2, is my result equal to 0? And in this case, it is. So we say yes, -2 is a zero. The other part of this is it said to determine whether -2 and 2 are zeros. So now we have to plug in a +2. This is your try it problem. Hopefully you found when you substitute a value of 2, the result to be a 4. Now again, we have to determine, is 2 a zero of the function? Well, did our result equal 0? No, which tells you 2 will not be a zero of the function. Example 4, find the zeros of g of x equals x plus 2 times x minus 4 times x minus 4. Since it said find the zeros, where you see the function, we replace that with a 0. So we now see 0 equals x plus 2 times x minus 4 times x minus 4. Since we have 3 values multiplying and the result is 0, one of those values has to be 0 in disguise. So the first value of x plus 2, well, what would cause that to equal 0? Well, that would be x equals -2. Looking at the middle value, x minus 4, what would cause that to equal 0? Well, that would be x equals +4. And the last value, x minus 4, what would cause that to equal 0? That would also be x equals 4. So in this case, our zeros are -2, 4, and 4. Now notice, the 0 factor of 4 repeated, which means we say it has a multiplicity of 2, while the 0 factor of -2 has a multiplicity of 1. So another way to write that, is we look back at 0 equals x plus 2 times x minus 4 times x minus 4. Wouldn't you say it's also another way to write it if I were to put 0 equals x plus 2 to the first power, because it's listed once, times x minus 4 raised to the second power since it's listed twice? Well, the exponents, the 1 and the 2, are also known as your multiplicities. It means how many times it's listed as a factor. Well, that fact brings us to this. If x minus c raised to the k power, where k is greater than or equal to 1, and is a factor of the polynomial function p of x, then if k is odd, then the graph crosses the x-axis at the point c, 0. If k is even, then the graph is tangent to the x-axis at the point c, 0. Now the key words are crosses and tangent. Well, because I want you to understand this, here's the visual representation. To cross means that the line or the graph will pass through the x-axis, and while tangent means something a little bit different. Tangent means it will touch the x-axis and bounce right off of it, kind of like a wall ball when you were a kid. It bounces off the x-axis. But in other words, the multiplicity determines if it crosses or is tangent. So let's look at another example. Example 5. Identify the 0, multiplicity, and the characteristic. So for A, we have p of x equals negative, parenthesis, x plus 3, close parentheses, raised to the power of 2, times x minus 4, raised to the power of 3, times x plus 1. So first it says identify the 0. That means we do need to set this polynomial to 0. So 0 equals negative x plus 3 squared, x minus 4 cubed, times x plus 1. Since we need to identify the zeros, we have to look at the individual pieces. We have 3 values that are all multiplying to give us a result of 0. The first piece is x plus 3. What would cause that to equal 0? Well, that would be x equals negative 3. For the middle piece, what would cause x minus 4 to equal 0? Well, that would be x equals 4. And for the last piece, x plus 1, what would cause that to equal 0? Well, that would be x equals negative 1. So we've easily identified the zeros, but now we need to identify the multiplicity. If you go back to the equation where it's in factored form, look for the exponents. For the first 0 of x equals negative 3, what is its multiplicity? Well, that's 2. We look at the next 0, which is x equals 4. What's its multiplicity? Well, that would be a 3. And then for the last one, x plus 1, what's its multiplicity? Well, in this case, you don't explicitly see an exponent, which means it's only listed one time. So its multiplicity is 1. Now that we've identified the zeros, the multiplicity, we're ready to identify the characteristic, which simply means, is this tangent or does it cross the x-axis? So our first 0, x equals negative 3, we say it has a multiplicity of 2. Since 2 is even, that means it will be tangent, which means it will bounce off the x-axis. For our next 0, we have x equals 4. Its multiplicity is 3. Since 3 is odd, it means it will cross the x-axis. It will pass right through it. The last 0 is x equals -1. It had a multiplicity of 1. Since 1 is odd, it will also pass through the x-axis. For example B, we have g of x equals x to the third plus 3x squared minus x minus 3. Again, we're being asked to identify the zeros, multiplicity, and the characteristic. So again, the first step to identify zeros, we have to rewrite this function notation set equal to 0. Now what's different about this function is that it's not written in factored form, so we will need to factor it. Notice we have 4 terms, and when you have 4 terms, we try factor by grouping. If I factor my first 2 terms and my last 2 terms, I will come up with 0 equals x squared times x plus 3 minus parentheses x plus 3. I notice x plus 3 is repeated, so I have a common factor. That leaves me with 0 equals x squared minus 1 times x plus 3. Although I have factored it, not everything's written in linear factors. Notice x squared minus 1. That can be factored again because that is the pattern of difference of squares. So in the factored form, that would give us 0 equals x plus 1 times x minus 1 times x plus 3. Now that we have all linear factors, we're now ready to identify the zeros. X plus 1 would create a 0 of x equals -1. The factor x minus 1 would create a 0 of x equals 1. And the last factor of x plus 3 would create a 0 of x equals -3. Now that we've identified the zeros, we're ready to state their multiplicities. So we look back at the factored form and we look at their exponents. X equals -1, what's its multiplicity? It's just going to be a 1. The next one, x minus 1, what's its multiplicity? It too is a 1. And the last factor, x plus 3, notice its multiplicity is also a 1. Now that we've identified the multiplicities, we're ready to state the characteristics. The characteristic depends on whether the multiplicity is even or odd. Notice the multiplicity is 1. 1 is odd, which means it crosses the x-axis. The next one, multiplicity is also odd, so it crosses. And the last one is also odd, which will also cross the x-axis. So we have completed this problem, but I want us to look a little deeper. Let's look for some more clues, some more things that we've learned and bring them back. So the other characteristics we're going to look at is going to be the degree, the in-behavior, and the y-intercept. So let's look at the degree. The degree simply means the highest exponent. If you look back at the original problem, the highest exponent was a 3. Next, we want to look at the in-behaviors. The in-behavior depends upon the leading term, the one with the highest degree. Since our leading term is x to the third, we notice that the degree is odd, and since it's odd, it means the in-behaviors go opposite directions. So we're envisioning down on the left and up on the right. But now we must check the sign. Since it's a positive x cubed, that means it will not flip, so our in-behavior will remain down on the left and up on the right. Next, we're going to look at the y-intercept. The y-intercept is where x equals 0, which simply means you plug a 0 in for every time you see x. Well, 0 to the third is 0. 0 squared is 0. So what we have is 0 plus 0 minus 0 minus 3. Well, all you're left with is the constant or the plain number, which means the y-intercept would be 0, negative 3. Now, let's put all this information together. So take the moment now to draw an xy axis. From here, let's plot our zeros or our x-intercepts. That'd be negative 3, 0, negative 1, 0, and 1, 0. Next, let's plot our y-intercept, which is 0, negative 3. So we've plotted all the points that we know for sure. Next, we're going to look at our end behaviors. We said that on the left side, our graph will go down. We'll find your leftmost point at negative 3, 0, and draw an arrow downwards. The other end behavior said on the far right side, your graph will be going up. So find your furthest right point, which is 1, 0, and draw an arrow upwards. Now we're going to look at the multiplicity and the characteristics. At negative 3, when x equals negative 3, we said that it would cross through the x-axis. So we're going to pass through the point negative 3, 0 and bring it to the next x-intercept. Now we have to decide at negative 1, 0, will it cross or is it tangent? Since it crosses, that means it will pass through and work its way to the next x-intercept. And at the last x-intercept of 1, 0, notice it does pass through. So this is a rough sketch of what this graph looks like. Notice it does pass through the x-intercepts at the points. It has the end behaviors. It shows the y-intercepts. So again, this is a quick representation of our polynomial function.